Swayam Prabha. Digital India. Educated India.
Yeah, say PTO damping, and this is radiation damping.
Then what's the expression of CPTO?
Okay, in such a kind of case, you choose this match, right? Say PTO equal radiation damping, right? Okay, okay. You set in the swing set, right? You with friends, whatever swing set, and if this swing to you, you don't push the force, right? When this guy leave, you give force. Why you do that? Right? Just that way, swing towards you. In such kind of case, you don't give force. It go, I go that way, right? In that way, every instant time, the force, time velocity is the power. Every instant time, I give power to the system. Is this clear? Wave energy converter is the same. Every instant time, you give power to the system. Then you take power from the ocean as much as possible. Okay, why there are two directions? Okay, so in coordinate, right? You say this real number, this virtual number, this virtual number, the two, there are 90-degree difference. Is this clear? Right? You just take a look at that way. This virtual number, this real number, the 90-degree difference. This is perpendicular, right? This is divided by j omega is negative j time, negative j time 1 over omega. So this is negative direction. Anyway, wave energy converter looks so complicated, but mathematically it's just so simple. Small mass system, cancel stiffness and mass, then choose the best damping. Okay, so that is what the physical meaning. Let us say the case study. Okay, then now you will appreciate it's not that simple. Okay, so let us say this one. The buoy is 5 meters. Okay, the draft means, what means draft? Draft is how deep this into water, right? The draft, let us say, is 5 meters. Okay, we want to match 10 seconds wave. This is very typical in California water. Okay, now suppose it's ball shape. So you can calculate the natural frequency 10 seconds. You can calculate the stiffness, added mass like that. So you will find for this one 5 meters, the mass is 33 tons. Okay, to achieve the resonance, ideal resonance, you have 450 tons mass. You need a huge flying wheel or huge gear ratio. The flying wheel and gear ratio translate into linear mass, right? So rotation inertia, let me say that way, take here. If you have ball screw, the lead angle is very small, and small rotation speed, so small linear speed, you change high speed rotation, right? Then you can achieve large rotation inertia, large mass. Or not only motor, use gear motor, you can put a gear ratio there, right? You speed up this gear by speed by 10 times, rotation inertia increase 100 times, right? So depending on the case, you may achieve such kind of large mass effect using small physical rotation flying wheel. Okay, so there's a risk, right? You may have larger gear ratio, then all kind of friction come up. Okay, so another thing I told you, and in addition to rotation inertia, maybe is achievable is not totally unrealistic. I will tell you what's not realistic. The vibration amplitude. Okay, so you already get the best stiffness cancelled. I told you at the beginning, when the system achieve optimal and CPTO damping will be same as radiation damping, right? And for this one, special case study, okay, and you can have damping like that. You plug all the parameter here, you will find your vibration amplitude 80 meters. Your bore is just 5 meters. 5 meter bore, you jump 80 meters up, 80 meters down. Not realistic, right? You think, wow, I do everything, I choose the best case. Wow, my boy jump out of water. Actually, nowadays you read some paper, a lot of people published paper, they didn't consider the stroke, right? They think, okay, mathematically is beautiful, right? And I already show you cancel everything like that. Now I choose resonance. Now when you calculate the amplitude, you plug this equation there, you calculate, man, my 5 meters bore plus minus 80 meters in the water. So all this mathematical beautiful things like, oh, linear damping, right? Everything's linear. No. Linear damping means linear wave theory, the amplitude is small motion. Now it's not small motion. Jump out of water like that. Once it's jump out of water, there's no hydrostatic stiffness anymore. Right? So you get a sense. Okay. So you may say, wow, can I limit my stroke? I don't want to have my stroke too much. What you will do? You add damping, right? You add damping, you can say my ball will not jump out of water. So, and also there's a physical limit, just like that way. This is your buoy. The buoy and ball screw, there's limited stroke, right? Suppose your stroke is limited. What you will do? So that is another topic we talk. Okay, 5 meter buoy, stroke 36 meters is not realistic. So now, and we want to say optimization of wave energy converter with limited stroke. So with limited stroke, you add the damping, right? And you have, so as we mentioned to you, right? You still cancel the stiffness effect. The only thing now, the damping, you don't choose the PTO damping. Sorry, you don't choose the PTO damping, you choose the PTO damping larger than the radiation damping. You first cancel the stiffness and mass. And we say maximum power output, you choose PTO damping to be the radiation damping. Now, I choose larger damping, right? So, you need to check if you have given limit or stroke, right? If this is given, okay, how large the PTO damping can be, right? You choose larger damping so that you limit the stroke. Is a vibration system like that vibration, now your damping you make larger, then the stroke is limited. Okay, so for the given stroke, you have maximum power output, right? Okay, so now we talk of everything. We talk everything about in this frequency domain, right? You cancel that. This cancellation is for given frequency. Is that true? It's for given frequency. Since at the given frequency, you can have given radiation damping, right? I mentioned radiation damping is very, very sensitive to the frequency, right? And also for the given frequency, you can calculate added mass. So that is for regular wave, harmonic single frequency, the regular wave. I told you, and most of the case you have certain spectrum, right? You have certain spectrum no matter well developed spectrum or not well developed spectrum, you have spectrum that is irregular wave. So for irregular wave, what you will do? You know how to design your PTO for the regular wave. Okay, you say regular wave look like most of the case, my wave is at this frequency, right? I can design for this frequency. For example, just now I said, okay, in US East Coast is 8 seconds roughly around that, but radio essence is the spectrum is not exactly 8 seconds, right? It is a range, maybe 5 to 10 seconds. Okay, I said 8 seconds most popular. I designed for 8 seconds. It's okay, nothing wrong with that. As an engineer, you know some regular wave design. You quickly choose all your parameters based on this frequency is fine. That is the first order design, right? And if you want to evaluate the performance to say that is good or not, so you can do that way, right? You understand single frequency. Now you put all kind of single frequency together, right? Here, one frequency, another frequency, all the frequency together, right, is a superposition. Here is amplitude, and here is one frequency, this amplitude, and you can use that way to calculate the spectrum delta omega times 2 square root, right? We know that already, right? So the only thing is in that time we may use different symbol here is fine. And when I put the natural nodes together, I didn't get a chance to work on the slides myself. Okay, so and like this slides, and is scientist in my group, Xiaofan Li, and he last year when I was in travel, he gave the natural, so his hand on writing. Okay, anyway, and that is for irregular wave case, right? You can choose the dominant frequency. You do first order design, right? And after that, you can take all the frequency together. You can do numeric optimization, fine tune your parameters. Okay, in ocean wave side, it's totally fine to have some very rough design and quickly engineering iteration, then use a high fidelity model for the calculation too. For example, potential flow, right? You can get the result in minutes calculation or half an hour. Do the quick iteration parameter design. After you get everything done, then you run NC's flow. You run the result 1 month later. You get the result to check. Okay. So, and if you run NC's, another thing you can set the viscosity to be 0. In that way, it's not a potential flow, but better than the potential flow, but run faster than the NS equation, Navier-Stokes equation. Okay, so this is for regular wave case. Okay, and the textbook, for example, here in Professor Falco textbook, he assumes that the PTO stiffness is 0. PTO inertia is 0, right? This is why in most of the reference book, you find this equation. They have, okay, just PTO stiffness, PTO damping. Actually, you have PTO mass effect or rotation inertia effect. So no matter what, so you get such kind of result that you match the natural frequency. Basically, you cancel the mass effect and stiffness effect, right? You match the damping, and your electric damping, which is a PTO damping, match radiation damping. Okay, in such kind of case, you get maximum power output. So, however, take a look at the figure here. That is frequency. This is how much is the excitation force. When we go this equation, when we do the derivative, whatever like that, you assume when the frequency change, you assume Fe is constant, excitation force is constant. So now you look at that, well, if I tune to this frequency, excitation force is not constant, right? So keep in mind such kind of design, even if you have such kind of design, keep in mind its approximation. You assume the excitation force is constant. Okay, so let us define another thing we called capture width ratio. Capture width ratio, you have buoy here, how much power to the buoy, right? We say the wave energy is measured by kilowatts per meter. You buoy here, this size will come to here. How much wave? That is kilowatts per meter times this dimension meter. This is input power to the buoy. Then I already told you how to calculate the output power. So output power divided by the input power, we define that as a capture width ratio. Is this clear? This is input power, output power relationship. Okay, sometime, I say sometime, or used or concept used popularly, but that is not correct, is hydrodynamic coefficient. Right? Sometimes I say, okay, this certain hydrodynamic coefficient or hydrodynamic efficiency. Okay, I put the buoy here, I get 50% energy out. I said this is hydrodynamic efficiency 50%. Sometimes we use that hydrodynamic efficiency as a word of capture width ratio. Which one is better? Which one is better word? Hydrodynamic efficiency or capture width ratio? Okay, let me tell you. Scientifically, capture width ratio is a good word. Hydrodynamic efficiency is a misleading word. Okay, so the reason is, if you use capture width ratio, you will find this number can be more than 1. So the input system that has 100 watts input to this system, output can be 200 watts. The way you calculate the input is not right. The reason is coupling, right? This fluid coupling in between. It does means, okay, I take the 100% of this energy out. This water will stay still, wouldn't move. Wouldn't be like that. Some other water surrounding that gives energy to the system. Right? So this is a theoretical number, how much the capture width ratio. If we have for this buoy, if move up and down, is symmetric body, capture width ratio maximum is wavelength divided by 2 pi divided by A. Right? You just imagine the way this is best case. The best case, they didn't consider this jump out of water. Right? So you just imagine that way. My wave amplitude, that's 80 meter, right? And divided by 2 pi, 80 divided by 2 pi, roughly 80 divided by is 12. Okay, so if my buoy size is 6 meters, right? And you will say that ideally capture width ratio can achieve 2. Right? In such a kind of case, you cannot say, well, I get 20% efficiency. right? You use efficiency word, this is misleading. Okay, it's still popular use for common talk. Oh, how much is hydrostatic hydrodynamic efficiency? Yeah, I get 80%, right? So actually, if you want to say scientific way, you say my capture weight ratio is 80%. Okay. So now, as you understand that, then you need to reduce radiation damping, right? People try different way to reduce radiation damping, right? You just imagine that way. Here, you radiation damping this contribution fluid separation, right? Here, this design to reduce the separation. This design so that the backside will not become wave maker. Okay, similar here, backside will not be wave maker. Okay, so we took a different way to enhance the power output using added mass, using flywheel rotation. Actually, we also can design your system. When you design the system, keep in mind, you can also play around the hydrostatic stiffness, right? So here, this one, your stiffness and this PTO stiffness, okay, you can have hydrostatic stiffness, okay. This expression and follow Professor Farkow's work. We didn't write the PTO's inertia here. Actually, you can write PTO's rotation inertia here. You can place this around, right? For example, as they say, most times the stiffness is too high. If stiffness is too high, I can make the damping, make the hydrostatic surface area, hydrostatic stiffness area small, right? Instead of merge water here, I merge water here. Which one have small stiffness? This now will have smaller stiffness. You can design for this, right? So I give you one example. So that is in this work is in collaboration E-Wave technology or startup company. So we would not design or wave energy converter. We use a power fish farm. Okay, so it take this shape. So it's inclined. What this inclined we try to do? The device is usually small. You want to reduce the stiffness. Reduce the stiffness, and the stiffness is cross section of the water, right? In this one, the cross section of the water volume, this 9. You put inclined this water surface, or you put say everything in the water. Just put this in the water, right? Then you will huge stiffness, right? Now I can put it this way. Stiffness becomes smaller. Make sense, right? So, or not. Actually, you can do that way too. This is shows one design. You have this mass. Let us say this mass here, and you cut this mass. The hydrostatic line surface here smaller. This point is this part is hinge. This part is hinge, right? Now I just cut this out. This water line here, then stiffness becomes smaller, right? So anyway, so not for wave energy converter design, there's a scientific physics behind, right? So this design, right? Initially, we thought about that, but we find that wow, the stiffness too high. Then we just tilt that. Wow, we match the stiffness. The behind that is just so simple. This equation. This is clear. So wave energy converter design, all the type of thing, you need to have some scientific mind inside, right? Design is us. Design is also science, right? For this one, initially we say, okay, we design that. Then we find out why it's hard to measure the frequency. Okay, we just cut that part. It's okay. Now we measure the frequency, right? When we measure the frequency, keep in mind there's A. What's A? Added mass. This part, the added mass is the same. Because when this move up and down, the water interaction wouldn't change much. So you still have significant large mass. Now you have smaller stiffness. Okay. And once until you guys ask this question, okay, Professor, why you only consider radiation damping? There are all kind of other damping. Right? And this fluid system, in the fluids are always viscous damping. There's drag damping. Right? Drag damping is second order damping, right? In this system, there are all kind of damping. So for the buoy on the surface of water, mostly the radiation damping dominate. The viscous damping is small. So for the buoy on the surface, okay, the radiation damping is dominate. This is why we only consider radiation damping. Okay, so if this under the water, in such kind of case, the radiation damping can be small, or viscous damping you need to consider. Yes, this is true too. Yeah, and
If you go for a larger diameter, then the power also.
yes, I think the more important thing is not viscous damping, is drag damping. Drag damping is proportional to the area. You go large, then you have large drag damping, right? So let us say different damping, right? Viscous damping, this shows the viscous damping, the force displacement loop. You have damper here, you pour that, and you have this type of force displacement loop. Okay, you have spring here. The force displacement loop is just a dash line. Just one spring. Spring F equal Kx, right? Now you have combination like that. You have both spring and damper. Then mostly you have this type of loop, force displacement loop. Okay. Another damping is dry friction. You have ball screw, you have rag pinion, or something touch that, you have dry damping, dry friction damping. By dry friction damping, force displacement look like this way. You pour like this one, you pour this direction, you have constant force, then this direction another constant force, negative constant force. At this end, when you're about to change the dimension, the force can be arbitrary between this negative maximum to the positive maximum, right? You measure your system, you find this type of shape, you know you have dry friction in the system, right? You find this loop is not a horizontal direction, you know you have stiffness in the system. Wait a second. You can also have mass in the system, right? Stiffness equal force is K times X, right? Mass, generated force, is negative M times omega square. So then you have mass, this system tilt to that direction. Spring cancelled, you return to this loop, this shape. Okay, so just now you mentioned that if my buoy increase large, then the drag damping be important. Drag damping is second order damping, where the damping force equal C times the surface area, right? So anyway, and you can have different surface area. Here this just shows one bore diameter. Okay, I like this figure. I want to tell you the fluid drag is related with separation of the fluid. You have large separation here, you have large drag, and you have streamline shape to reduce the separation, then you will have smaller drag, right? Smaller energy loss. So just imagine that way, this buoy, right? You can have cone shape under the inside the water, then reduce the drag, right? Also reduce the separation, right? This is how the Berkeley's wedge work. Okay, come here to Berkeley's wedge again. I want to write this shape, and this is one wedge. Actually, Professor Young also did some experiment with simulation with buoy, this shape, right? Instead of flat shape, and you have flat shape, you can imagine that way there's a lot of water separation. Then you will have large drag damping. Okay. So, and when we talk about drag, and since this is marine energy cost, it's not a wave energy cost, and we have to mention about wind and water turbine. And if time allow, I will cover a little bit, or Professor Samet will cover a little bit about wind and water turbine. Okay, when we talk about turbine, and here drag and lift, right? And we are going to, I gave this figure to you, and but you guys can understand here. And this turbine rotation, there's a rotation speed, right? And there's wind speed in this direction too, right? This total wind to this direction, this is wind combined direction. So along this direction, that is drag. Perpendicular to this direction is lift. Okay, so after that we talk about tank test. Okay, and let us continue. Okay, and I'm going to talk about tank test, right? And when you do the model in the tank test, as you say in the ocean, you have huge wave, non-wave length, but in the tank you cannot build such a large device. So your device is small, right? How to make your device representative, right? That is what we talk about, Froude number. And Froude number, there's a scaling law. Basically, for example, if you build a 1 to 25 scale device, right? And your 4 scale 12.5 meters, you want to build 0.5 meter, right? 25 scale. Okay, 25 scale, how to scale the wave period? Okay, wave period is not scale 25, it's scale square root 25, 5 times, right? If you have wave period 10 in the ocean, in tank test, you put a 2 seconds wave, right? So this scaling of frequency. And power density scaled by 10, let us say 25 power 2.5. The scale very, very quick, up or down. And actually, is scaled, this scale is based on Froude number. What Froude number? Froude number itself, there is inertial force divided by gravitational force, right? That has been used for the tank test, including the boat test, ship test, and also whale, offshore wind structure, all the type of things that use Froude number. Like this one, we build here, this is 1 to 10 scale. If we build 1 to 10 scale, you need to scale the wave, and wave height can be scaled linearly, but wave period and wave density is scaled at different scaling law. Okay, so this is how you do the tank test, and this is similarity. That means you follow this law, you can predict the full scale system. Okay, so for example, like this tank, right? And if this one is 4.7 meters, right? If you scale 1 to 10, this corresponding or ocean side 47 meters, like that. Okay. Let us say this one. Take a look at the power. Okay, the power scaled by S times 3.5 times. Let us say that way. Let's give one example. If your 4 scale system is 22.5 meter, right, is roughly quarter wavelength. Okay, and this device you may design for 300 kilowatts. Okay, now you scale down 1 to 20, 1 to 30. Your device is 0.75 meters. 0.75 meters is pretty large device in the tank. So, right, and if your ocean well is 2 meters, after you scale 1 to 30, it will become 67 millimeters, right? And it's this much, right? So now your well, let us say, is 9-second well, according to well frequency scale down, you become 1.6 second well. Now you use the power 3.5, this scaling law, 300 kilowatts device, you become 2 watts. What does this mean? The ratio scaling is internal power scaled by 1 to 150,000. That ratio, what does it look like? You have soccer field and the earth. That's the relationship, right? Look like now you are doing the tank test. You already built this type of device. The feeling is you study in the soccer field, you try to understand the earth. You can say the scaling law, what kind of influence, right? Therefore, it's very challenging, right? You already built a pretty large device. Now, the power is just 2 watts. 2 watts power is very, very small, right? And just power your cell phone needs 1 watt. So, as a result, so if you have 2 watts device, all the friction, whatever, can be dominated. So, on auto sense, you scale down, then friction become more important. So that is the challenging part of wave tank test. And for some system, if you don't involve the mechanical transmission, it's totally fine. For example, alternating water column. Alternating water column, you guys are going to do experiment. Okay, it's a bucket upside down, there's a hole here. You can see air in and out. For that one, it's totally fine, no whatever 1 to 30 scale. But if you want to reproduce such kind of large mechanical system at a smaller scale, the friction is important. Okay. So you guys also learn Reynolds number. You guys remember Reynolds number, no? Reynolds number, probably you remember this equation, right? Rho V D mu, right? Real number, the physical meaning is inertial force divided by viscosity force, right? This is inertia, this viscosity force. Okay, so Faraday number is the inertial force divided by gravity force. Okay, so my question is, both are kind of similarity, right? You do the pipe flow study, right? You try to match sense in Reynolds number or whatever like that. And my question is, when we do experiment study about similarity, can we keep both numbers the same scaling law? Can we use Faraday scaling law and Reynolds scaling number? It's hard. These two are totally different. Which number we should use? I just now tell you we use Faraday number. Why we didn't use Reynolds number? Or this wave theory we discussed so far, we didn't consider viscosity, right? Radiation damping, added mass, all these concepts come from potential flow. So for this reason, which one you are going to use? Reynolds number, there's a viscosity force there, right? Faraday number, just inertial force, right? Faraday number is good enough so far for the wave energy study, right? And unless you have to consider viscosity, right? And as I explained to you, and for the buoy, the type of thing on the surface, and radiation damping dominate much larger than viscous damping. Therefore, you don't need to consider the real number. Okay, and keep in mind how to scaling up, scale things down. Okay,